welcome, and thanks for coming to the Carl Sagan Center SETI Institute Lunchtime Colloquium Series. For anyone who's new, we have these talks every Wednesday at lunchtime. We have a wide variety of speakers on topics that include astronomy, biology, geology, physics, basically anything to do with space science, life in the universe, and the various and myriad missions of the SETI Institute. So before I tell you about today's talk, let me promote next week's, which will be Tom Abel, who will speak about first things in the universe. So that will be much more on the astronomy, astrophysics side of things. We do record these talks. You'll notice the camera. And we archive the videos up on our website. If you go to www.seti.org and click on the picture of Frank Drake that says Scientific Lectures, you'll get to the Colloquium homepage. From there, you can subscribe to our email list. The email list will send you announcements of upcoming talks. And also on that page, you can see the archives of former talks. You can download the videos, you can download the slides, you can read the abstracts, and see how exciting they were, and not have to miss out on them. And so because we do record these talks, I ask that you try to hold your questions until the end of the talk, so that I can run around and give you this microphone. That doesn't amplify your voice, but what it does is it allows us to capture your talk into the audio of the video archive that we'll make. And so if you do need to ask questions during the talk, try to be brief. If you're going to be long, I'll try to just bring you the microphone so that we can work it that way. But it's better to wait till the end of the talk if you can. And so, without further ado, let me introduce today's speaker. His name is Jasper Halekas. He's from UC Berkeley's Space Sciences Laboratory, and he's a research scientist there. And he received his PhD from Berkeley in physics, and he did his undergraduate work at the University of Washington in both physics and math. And today he will speak about the dynamic lunar environment. Thank you.
All right, thank you very much. Don't clap yet. Thanks for coming today. Last time I gave a seminar, it was on Inauguration Day, and today it's Tax Day. So I'll let you draw your own conclusions on which is a happier occasion. But if you forgot that today is Tax Day, now's your last chance to run screaming out of the room. So I'm going to be talking about the dynamic lunar environment today, and I'm going to explain what I mean by that. Since the dawn of the space age, we've learned a lot about the moon. We've learned that it's not just a cold hunk of rock sitting up in the sky. We've learned that it's not made out of green cheese. In fact, we've learned how to view it with a lot of different eyes. For instance, we've learned how to look at the moon in terms of topography, geology. This is a geologic map made in the Apollo days. We've learned to look at the moon in terms of gravity, in terms of elemental composition. This is a thorium map. But all of these views of the moon are kind of static. There's nothing changing here. You could take this same snapshot now, and you could take it again in 1,000,000 years, and it would look exactly the same. So what I'm going to be talking about today is a view of the moon which is very decidedly changing and very quickly. And this is kind of the moon as seen by a space physicist, if you will. And it's not a static, unchanging environment that is the same from moment to moment. It's very dynamic, and it's changing a lot. And the reason for that is that the moon is sitting there immersed in kind of this soup of plasma and photons and all these energetic inputs from the sun: photons, solar wind particles, energetic particles, coronal mass ejections. It also passes through the Earth's magnetosphere and is bombarded by a variety of different plasma sources there. And all of this stuff makes the lunar environment, especially right near the surface, very dynamic. It's kind of just bubbling and seething. As my colleague Bill Farrell likes to say, the lunar surface literally percolates with activity. And the reason it does is that it's being bombarded by these charged particles and photons. This causes the surface to charge up. It generates neutral exospheric constituents. The moon, though we all know it doesn't have an atmosphere, it has a little bit of an exosphere. There are some gases around the moon. These gases can be ionized, form pickup ions. They could be lost from the moon by a variety of different processes. There's dust, we think, levitating above the surface of the moon in places and at times. There are small little magnetic fields around the surface of the moon which perturb this basic picture. And there's a really interesting wake region downstream of the moon. As the solar wind goes streaming by, it leaves this void in the plasma. And as the plasma tries to fill in that void, some very interesting plasma physics happens. So today I'm going to kind of go through and talk about a lot of aspects of this lunar environment. especially the dynamic parts. And so this is just kind of the outline of what I'm going to be talking about today. I'm going to start with the exosphere. I'm going to talk about the wake and the solar wind. I'm going to talk about some of the interesting things that happen when all these plasmas flowing by the moon hit these little crustal magnetic field regions. And then I'm going to zoom down into the very surface and look at what happens right at the surface interface as photons and plasma interact with the lunar regolith. And finally, I'll say a little bit about the future of lunar science and maybe a little bit about Mars science too, if I have a chance. So I'm going to be showing a lot of the data that I'm going to be showing today is from the Lunar Prospector spacecraft, which was built by, among other people, Ames and Lockheed Martin. We had an experiment on there, we being Berkeley, which was the magnetometer electron reflectometer experiment. The magnetometer is a standard 3-axis flux gate magnetometer, which just measures the vector magnetic field. And the ER is an electrostatic analyzer, which measures electron distributions as a function of angle and energy. And using these two instruments, we can measure a variety of interesting things at the moon. I actually started out as a grad student at Berkeley using this data to look at crustal magnetic fields, of all things. But I'm going to be showing you a lot of other things that you can measure with this data today. I'll be sprinkling in data from a variety of other missions that have gone to the moon, including as far back as the Apollo days, the Explorer 35 and Apollo subsatellites, some interesting flybys of the moon by wind and geotail. And I won't show you any data, but there was actually some really nice lunar data from Nozomi, which was a Mars mission, but happened to fly by the moon and make some very nice measurements before it was lost. Never actually made it to Mars. So we have lunar data from that. So let's start with the exosphere. This is not an image from a spacecraft at all. It's an image from the ground from a telescope. And what this is showing is sodium D-line emission. And this is this interesting neutral exosphere that the moon has. It's very faint. It's not an atmosphere because the mean free path is longer than the scale height. So basically, it's not collisional at all. It's produced at the surface, and it just goes flowing off into the cosmos. But there's enough of it there that you can see it very brightly from the Earth if you look at it in the right wavelength. And so this is it's a really interesting kind of thing. There's a number of processes by which we think this exosphere may be generated and by which it is lost, but we don't yet know what are the most important processes. This is just kind of a schematic of some of the different ways that you can create an exosphere. Basically, anything that you hit the surface with some probability you'll knock off some gas. So if you hit the surface with photons, charged particles, micrometeorites, you can create a little bit of an exosphere. There's also a number of other things that can happen. Just thermal desorption. You rotate a shadowed area into sunlight. You heat up enough of it that some gas can come off. There's some suggestions that there are outgassing from active sources, from volcanic kind of processes on the surface. There are chemical sources. There are a number of analogous losses as you rotate a sunlight region into shadow. Some of this stuff freezes out back to the surface and adsorbs to the surface. There are chemical processes. A lot of the stuff that gets up into the space is just lost because it exceeds the escape velocity. So that's kind of Jean's escape. And a lot of the stuff that gets up into space also eventually gets ionized by charged particles or by photons, and you get pickup ions. And so this stuff gets ionized and it flows away downstream with the solar wind. So we don't know exactly what the importance of these different processes is for sodium, and we don't know what it is for all the other species. It may be very different for sodium and for other species. The sodium image that I just showed you is very pretty, but sodium is just a trace species in the exosphere. It's not even one of the most abundant species that we have. There's also a lot of dynamical variation, as you can imagine, on a diurnal time cycle. This is a model by Dick Hodges showing the moon at two different altitudes. This is higher altitude, lower altitude, and showing what happens to the exospheric density of a species such as argon as the moon rotates around. And this is kind of dawn here. This is dusk over here. And you can see that all this stuff freezes out on the night side, and then as it rotates out into sunlight, there's a big release of this gas up into the exosphere. And so you can get some really fascinating dynamics and really solar zenith angle dependent behavior here, really more local time dependent behavior here. This is another beautiful image of the sodium emission. All of this exosphere is coupled to the surface in interesting ways. As charged particles, which generate some of this exosphere, hit the surface, they actually weather surface by depositing, little bits of vapor by sputtering parts of the surface, and you can actually change the optical properties of the surface by impacting it with enough solar wind, charged particles, and so forth. You can also deposit volatiles on the surface. Dana Kreider has done a lot of really interesting work about what happens when you deposit a little volatile on the surface, like, say, a little water molecule. Well, it turns out that it's not very well bound to the surface, and with some probability it hops off of the surface. And these little water molecules will hop around the surface until they get someplace that's cold enough that they stick. And so we may actually have little cold traps of water up in these permanently shadowed regions near the poles, as suggested by this image of hydrogen from the Lunar Prospector spacecraft. It's actually an image of neutrons, but the low in neutrons here indicates that there's absorption by hydrogen, which may be water. So this exosphere is coupled to the surface in interesting ways. It's also coupled to space in interesting ways. As I told you before, these exospheric constituents can be ionized by photons or charged particles, and once they are, they're picked up by the electric field of the solar wind, and they're swept downstream, and you can measure them a long, long ways from the moon. This is data from the WIND spacecraft, and don't worry about the details of this. Just believe me that this is a detection of lunar pickup ions, which are some tens of thousands of kilometers away from the moon. In fact, close to 100,000 kilometers away from the moon, upstream of the Earth's bow shock. So these pickup ions from the moon go streaming off downstream, and you can measure them a long ways away. We think if you can measure them up close to the moon, you can actually use this as a really sensitive technique to measure the surface composition and things like that. But no one's been able to prove this technique yet. So while I'm talking about space and ions and plasma and stuff, let's talk about the Lunar Wake a little bit. So the Lunar Wake is a really interesting region because when the moon is out in the solar wind is streaming by, it's moving at supersonic speeds. You might think that this would be something like a jet moving through the atmosphere where you have a big shock wave out in front and so forth. But it's not, because the solar wind just doesn't even see the moon until it hits the moon. The solar wind hits the moon, it's completely absorbed by the surface, with the possible exception of regions where there are magnetic fields. But that's kind of a secondary complication. The moon is absorbed, and it leaves this complete cavity in the plasma behind the moon. It's actually perhaps one of the best natural vacuums in the solar system. And as the plasma goes streaming by, it suddenly sees this discontinuity here. There's plasma on this side, there's no plasma on this side, and so nature, abhorring a vacuum, wants to fill in this wake region. But because the plasma is not all one fluid, it's composed of ions and electrons, it fills it in a really kind of interesting manner. What happens is that the electrons are lighter and therefore faster, and they can kind of rush ahead and try and fill in this wake region. The ions are kind of slow and lumbering along behind, and they don't fill in as fast. And this creates a charge separation. So there's negative charge inside, there's positive charge outside, and it sets up an electric field, which slows down the electrons and speeds up the ions, and you get this kind of weird push-pull kind of infilling of the lunar wake, with the electrons leading a little bit, but then the electric field says, no, wait for us, and the ions come along behind. And so you get some really interesting electric fields and beams of ions and so forth formed as the plasma fills in this wake region. As you can imagine, this creates a host of electromagnetic instabilities, waves, and a lot of things which we're still trying to understand.
Can I ask a question?
Yes?
Nature abhors a vacuum is a wonderful term, but can you say a little more about what forces are actually causing these things to move, the ions to move into this?
Absolutely. It's a pressure gradient, basically. That's
Depending on there being electrically
No, it doesn't depend on it being electrically charged. If you had a non-charged fluid flowing past the moon, it's still going to slowly fill in this wake region. That's a good question, though. This picture would be very different in a lot of ways if it wasn't a charged fluid. If it was just a neutral fluid, you wouldn't have any of these sorts of electric fields and currents and so forth. It would just be more like the wake behind a boat, moving at high speed or something. But because it is a plasma, there's a lot more going on. So we have a lot of measurements of this. This is actually a simulation, but it just shows that the influence of this wake region propagates downstream quite far. This color scale shows density in kind of a weird inverted color scale, where the red is low density and this blue is the background density. But you can see that this wake is expected to propagate downstream to quite long distances. This box is something like 30 lunar radii long. And you can see there's this clear void here, but downstream there's a lot of kind of wave-like structure to what's going on. So this is a variety of observations from the WIND spacecraft as it went through this wake, probably right about this region here, 6 lunar radii. And you can see that there's this large dropout in the proton density, the electron density as well. There's actually an increase in the temperature of the plasma in the void, and I'll speak to that in a little bit. There's a slight signature in the magnetic field. This is magnetic field magnitude here and various components. And you can see there's a slight increase in the magnetic field in the wake. I'm going to talk about that in a second as well. And there's also a variety of wave activity. As you actually go into the lunar wake here, this is a frequency spectrogram of electromagnetic wave activity. The waves all drop out when you go into the wake. But if you look at this high frequency stuff, when you're actually connected to the wake, when you're out here somewhere but the magnetic field is pointing to the edge of the wake, you're picking up all these electromagnetic instabilities caused by this infilling of the wake. And so this is all quite far downstream. With Lunar Prospector, we got to see this stuff right up close. Now this is a projection basically of a shell around the moon, just stretched out and spread flat and centered on the wake. So this is the center of the wake here. This is the wake boundary. All this stuff is upstream from the moon. And this is showing electron density and temperature. And you can see when we looked at 6 lunar radii, there's a dropout in the density of about an order of magnitude or so. Now when we're at 100 kilometers altitude, there's a dropout in density of something like 4 orders of magnitude. This really is a great plasma vacuum. And there's also this really interesting large increase in the temperature of the electrons. The reason this happens is because you're just basically letting just the tail of the electron distribution get into this wake region. And so it's only the hottest particles that get in there. And so you get a large increase in the effective temperature of the plasma in the wake. And that turns out to be important for some of the electric fields and stuff that I'll be talking about in a little bit. Also interesting things happen to the magnetic field. This is basically a delta of magnetic field now. It's the magnetic field that we measure around the moon with the solar wind component measured upstream subtracted. And you can see that there's this enhancement of magnetic field in the center of the wake, just like we saw in the wind data further downstream. And there's this depression around the edge of the wake. And there's a couple different ways that you can think about this. One is that there's a current system produced around the wake boundary as a result of the pressure gradient. The other way to think about it is kind of more in fluid terms. As the plasma slowly expands into this wake region, it pulls magnetic field lines with it. So as the plasma expands from outside across this wake boundary, it stretches the magnetic field lines apart in this region. And so you get weaker fields there, and it compresses them together in the center, and you get stronger fields there. And it turns out that this increase in magnetic pressure in the wake is just enough to balance the decrease in plasma pressure. So it works out very nicely. This is at about 100 kilometers altitude. We can go down even further. Lunar Prospector got down to actually we got down to about 17 kilometers at the very lowest, but we averaged something like 30 kilometers for our last year. And this is the same kind of plot. You can still just barely see a wake signature here, but it's very noisy and disordered. If you plot this same data in a geographic coordinate system instead, all of a sudden you see that there's some order to it. There's actually patches of strong field and patches of weak field. And this, of course, is a result of the crustal magnetic fields on the surface of the moon. The moon has no global dipole magnetic field like the Earth has, as you know, but it does have these little patches of magnetized crust, and they're very non-uniformly distributed, as you can see here. You can use some techniques to clean this up, and you can get a view of what just the crustal magnetic field signature looks like. This is near side and far side showing the magnitude and the theta and radial components of the crustal magnetic field. You can see that it's very non-uniformly distributed. There's big, strong patches on the far side and on part of the southern and eastern near side, but not very much over here, not very much up here in the North Pole. And when you zoom in and you look at the polarity of these crustal magnetic fields, they're just wobbling all over the place. If you're on the surface of the moon and you have a compass, it does you no good at all. You're walking around and the compass needle is going around like crazy. In fact, they did this in the Apollo days. They took a magnetometer around and did measurements a few kilometers away from each other. And even on a scale of a few kilometers, the direction of the magnetic field is completely different. It's just completely disordered at all scales. So the interesting question for us is what happens when the solar wind hits this crazy jumbled up magnetic field? Do you see something like you see in the case of the Earth, where you get a big coherent bow shock and the solar wind is deflected away from these things and you have a region shielded from the solar wind above these crustal magnetic fields? Or are they so small and jumbled that instead you just get a bunch of kind of random turbulence generated upstream from these things? Well, there's some simulations that give us a clue of what we might expect to see. What these people did with their simulation was they just took a little magnetic dipole and they stuck it out in the solar wind, and they ran some solar wind plasma by it and saw what happened in their simulation. And then they increased the size of the dipole larger and larger and larger to scan kind of different regimes of solar wind interaction. So what they saw was that when they had a tiny little magnetic dipole, very, very small standoff distance in the solar wind, they basically just rattled the electrons a little bit. The electrons are smaller and more mobile, so they can kind of see smaller scale things. And so when they had a small little dipole, it just created a little Whistler wake. These whistlers are kind of electron scale waves. But the plasma as a fluid didn't really do anything. There's no real change in the plasma density as you go by. If you bump up the scale a little bit more, in addition to this Whistler wake, you start creating magnetosonic wakes. And what this means is that you're starting to rattle the ions a little bit, as well as the electrons. And now you can see that there's a dropout in the density downstream of this obstacle. There's a little bit of a wake downstream of this little dipole magnetic field. If you boost up the strength again, now all of a sudden you've got something. You form a big bow shock upstream of this crustal magnetic field. There's a huge enhancement in the density there. There's a big wake downstream. It's starting to look like something like the Earth's magnetosphere, but not quite. There's not nearly as much structure. If you bump things up another order of magnitude still, then you get something that looks like the Earth's magnetosphere with all the interesting structure that we know and love. If you look at what the scale of the crustal magnetic fields on the moon is, you shouldn't see either of these last two cases. You should basically see one of these kind of modes of interaction where you just see some waves, maybe a little bit of a wake formed in these little magnetic field regions, but you shouldn't see anything like a big shock upstream. So this is the theory. Let's see what we actually see. Turns out we see everything under the sun when we go across these things. Here's a case where we just see turbulence. This is the magnetic field at high time resolution, at low time resolution, and this is a frequency spectrogram of the magnetic field turbulence. And at low time resolution, you can see we're flying along here. We see some crustal magnetic fields here. We see one of these big dips in the magnetic field as we fly across the wake boundary. Everything looks pretty normal, but if you zoom in at high time resolution, the magnetic field is just ringing. It's just ringing like crazy. And this is not something intrinsic to the crustal magnetic field. It's something that the solar wind is doing as it sees this magnetic field in front of it. It's seeing this magnetic field and the plasma's going crazy and it's just ringing like crazy. And you can see that it's broadband turbulence. It's all over the place. Whenever you're magnetically connected to the surface, whenever there's a crustal magnetic field, the whole plasma is just ringing. This is a case where it's really incoherent. There are also cases where it's really coherent. Here again is another magnetic field pass. There's a big feature here where we go over a strong crustal field. There's another one of these dips as we go across the wake boundary. And here's a bunch of wave activity when you look at the frequency spectrogram. And you can see here that it's monochromatic. It's just at one frequency. If you look at a cut across here, you can see that it's really strongly peaked in power at one frequency. If you look at the actual waveforms, it's really completely sinusoidally varying. And if you look at how the magnetic field rotates as you go through it, it rotates in this circular fashion. So it's a really coherent, circularly polarized wave. And this is a sign of some kind of coherent process at the bow shock, at perhaps something like a bow shock, even though the simulations would say there shouldn't be something like that. Here's one where we actually see the shock itself. This is an electron energy spectrum as a function of time. So the color tells you the flux. This axis is energy. Here's the electron density, the magnetic field magnitude, magnetic field, one of the components, and another one of these frequency spectrograms. And you can see as you fly across this thing, you're flying through here, you see a little upstream wave activity, some electron heating, and then you hit this huge shock ramp, and the magnetic field goes way up, and the electron density goes way up. And this is exactly what you expect to see at a bow shock. It's exactly what you would see if you flew across the bow shock upstream of the Earth's magnetosphere or Mars's magnetosphere or any magnetosphere. So despite the fact that the simulations tell us we shouldn't see anything like this, it looks an awful lot like a big bow shock. So another really interesting thing is that it depends on what the solar wind conditions are. You can fly across exactly the same region at different times and see completely different things. This is 2 passes over a north polar region of the moon on consecutive days with very different solar wind conditions. So the first time you fly across here, you see a very coherent kind of shock-like structure. You see very monochromatic upstream electromagnetic waves. The second time you fly across here, there's nothing but turbulence. There's no coherent shock structure. It's just completely turbulent. So what happened? Well, the solar wind velocity went way up. The solar wind dynamic pressure went way up. So it may just be that the solar wind was strong enough to just compress this whole interaction region below the spacecraft. So the first time we went through here, we saw a shock, and we saw all this interesting kind of upstream stuff. The second time we went through here, the solar wind just compressed it right below us, and it was too low in altitude for us to even see anything. So you have this interesting case at the moon where there are magnetic fields of varying scale sizes. The solar wind has varying properties, and it actually allows you to scan out a variety of different regimes of interaction. So it's really kind of a little physics lab up in space for looking at how the solar wind interacts with magnetic fields of different sizes, because we see the whole range. So back to this question, do we see something like a mini magnetosphere? Well, we see something like this upper orbit where we've gone across and we see a big bow shock. But do we see something like this lower orbit where we actually go into a mini magnetosphere of the moon? Well, it's not really clear that we do. There's one case in the Lunar Prospector data that looks like it might be something like this, but it's not quite what you would expect to see. However, there's some indirect evidence that these do exist. Now, this is just an optical image of the surface of a feature called Reiner gamma, and I've put contours of crustal magnetic field strength above it. And what you see is that there's these very interesting optical features. They've been variously termed swirls or optical albedo markings. Everybody has a different name for them, but they're basically these patches of very light material on the surface, and they tend to have very weird kind of contorted morphologies like this one here. And it turns out that these things correlate almost perfectly with crustal magnetic fields on the surface. Everywhere you see a strong crustal magnetic field region, you see these interesting albedo markings. So what in the world is going on here? Well, some people think that what's happening is that a comet has impacted the surface of the moon, and it's created both the albedo marking and the magnetic field. So that's one possibility. But another possibility is that however these magnetic fields were formed, they're strong enough that they're actually deflecting the solar wind away from these regions of the surface. And remember I told you earlier that the solar wind can change the optical properties of the surface by this solar wind weathering process. So maybe what's happening is that these crustal magnetic fields are deflecting the solar wind away from these regions of the surface, and they're just not being weathered as much as the regions around here. all these regions outside of here have been weathered by the solar wind and darkened over millions and millions and billions of years. These regions here have been completely protected from the solar wind. So this is by no means an open and shut case, but it's a possibility that there is actually something like a little mini magnetosphere here that's protecting these regions of the surface. So while we're on the surface, let's talk a little bit more about what happens right at the surface. This is a figure that we made for a proposal actually years ago, and it's been transported so far and wide it actually showed up in a NASA report. I've also seen it in other people's proposals over the years. But anyway, what this is showing is basically what happens right at the surface of the moon when these charged particles and plasmas are impacting the moon. What happens is that the surface charges up, and it charges up because the moon, like a spacecraft or anything else in a plasma, wants to charge so that the currents to the surface are balanced, or equivalently so that the potential of the surface is minimized. Those turn out to be basically the same proviso. So what happens is that on the day side lunar surface, it's being bombarded by both photons and charged plasma. The photon flux generates photoelectrons from the surface. It's the photoelectric effect. We all know and love it. It turns out to be very efficient. You get tons and tons of photoelectrons generated from the surface of the moon. The flux of these photoelectrons is way bigger than the flux of any ambient plasma. So the moon charges up positive in order to attract most of these photoelectrons back to the surface. The moon basically doesn't want to be an electron gun. It doesn't want to shoot off a huge current of photoelectrons into space. So it charges up positive in order to attract these guys back. And it doesn't have to charge up very positive because photoelectrons aren't very high energy. So it charges up to sort of plus 5 or 10 volts or so on the day side. On the night side, on the other hand, there are no photoelectrons. No sunlight, no photoelectrons. So it's just the plasma that charges the surface. It's just electrons and ions. And so what happens back there is that similar to the Wake case, the electrons are lighter and faster. They tend to dominate the dynamics of what's going on. There's a higher flux of electrons. And so the surface will charge up negative in order to repel most of these electrons so that the ions and the electron currents can balance. And it turns out that it charges up to sort of the order of the kinetic temperature of the electrons, which is not too big most of the time. In the solar wind, it's very small. It's 10 or 20 electron volts. In the Wake region, because of this increase in temperature that I showed you, it's more like 100 volts or so. And that's typically what we observe is about 100 volts negative on the night side. However, there are times when we see much, much hotter plasma around the moon. One of those is when we go through the Earth's magnetosphere. Another is solar energetic particle events. So I'm getting a little ahead of myself. Here's the Earth's orbit, viewed edge-on and viewed kind of from the top, from the North Pole, if you will. And so you can see that the moon spends about a quarter of its time in the Earth's magnetosphere, and the rest of the time it's out in the solar wind. And this is important for the charging because when it's in the Earth's magnetosphere, it goes through this very complicated kind of magnetotail structure back here, and it encounters this thin region shown here in yellow, which is the plasma sheet. And this is the region on this side of the Earth's magnetosphere. The magnetic field goes one way. On the other side, it goes the other way. In between these lobes of oppositely directed field, there's this very turbulent region of energetic plasma called the plasma sheet. The rest of the time, it's out in the solar wind. Not much happens out there most of the time, except at times when the sun gets it in its head to have one of these huge coronal mass ejections. And at times when these happen, none of them have happened lately because we've been in like the longest, craziest solar minimum in history. But at most times, you can have these huge coronal mass ejections. The sun just burps out a bunch of big, hot ionized gas, and you can get very energetic particles from that. So what does that do to the moon? Well, if you look at when the night side of the moon charges up really, really negative, and you can plot it as kind of a frequency histogram. So every time this bar goes way up, that's a day when the moon charged really negative a lot. And you plot it as a function of time, you can see that there are times when the moon charges negative to very high values, and there are times when it's much, much, much quieter. I've set the threshold here at 500 volts negative surface potential. So then you can plot down here in this little color bar and try and make sense of this. Every one of these green bars is when we go through the Earth's magnetotail. It's very regular. It happens once a month. Each one of these red bars is when we hit one of these big solar energetic particle events, one of these coronal mass ejections from the sun, energetic particles streaming out, impacting the moon. And you can see that the moon and its extreme surface charging properties is completely correlated with these two things. Basically, magnetotail crossings and solar energetic particle events explain the whole distribution of large surface charging that we see on the moon. So I just want to zoom in a little bit at those two different cases. Sorry for all the squiggly lines here. What I'm showing here is a series of Lunar Prospector orbits through the terrestrial magnetosphere. So this is when it's back in the Earth's magnetosphere in the tail. This is the spacecraft potential. This is the electron density, the electron temperature, and the surface potential of the moon that we measure using Lunar Prospector electron data. And these bars just show you when you're in sunlight versus in shadow. So each one of these sunlight shadow bars is essentially one Lunar Prospector orbit as it goes in and out of shadow. And the one thing that I want you to take away from this is if you look at the electron temperature here, and you look here, it's very, very cold. We're in the tail lobes. It's this very calm, quiet region of low temperature electrons. Then you go into the plasma sheet, and the temperature goes way up. And then we're back in the lobes. Plasma sheet, hot temperature. You look down here at what's going on with the lunar surface potential, and it's perfectly correlated with this. Every time we go into the plasma sheet and we get one of these big populations of hot electrons, the lunar surface potential goes way, way up. There's a little complication here because most of the time you only get large negative charging when you're at night. Sometimes in the day, but mostly just at night. But it's really, really well correlated with what's going on in the plasma. So this is one of the times when we see large surface potentials. The other is solar energetic particle events. So more squiggly lines, sorry. This is low energy electrons that we observe in situ with Lunar Prospector. The reason it's really, really spiky is that the spacecraft is going in and out of the wake, in and out of the wake. The density goes way down in the wake and then back up when you're in the solar wind. And then these are the upstream energetic particles. So this shows you basically what's coming down the pipe from the sun and hitting the moon. And you can see that there's these two huge injections of energetic particles during this time period. And if you look down at the lunar surface potential, this is magnitude now. These are actually negative potentials. You see each time one of these big spikes of energetic particles hits, the surface potential of the moon goes way up. And we got up to 4.5 kilovolts negative here on the night side of the moon, which is the largest potential we observed with Lunar Prospector. But maybe not the largest potential ever seen on the moon. Who knows? If you zoom in on one of these little things, I've actually just shown the peak potential for each orbit here. There's actually a lot of variation on each orbit. You can see as you go into the wake, the potential goes way up and then kind of comes back down as you go out, way up in the center of the wake and back down. The reason for that is that it's hard for the low energy plasma to get into the wake. As we saw, it's this kind of void of low energy plasma, but the energetic stuff can get in there, no problem. It's moving so fast, it has such huge gyroradii that everything just gets in there. So in the center of the wake, these energetic particles totally dominate, and the surface potential can spike way up. So we've done a little bit of work trying to model what's going on. These are the energetic particle inputs again for just one of these injections. This is the data, and this is our model, just showing that we basically know what the physics of what's going on here. It's just current balance. That's all it is. Whenever there's a huge influx of energetic electrons, the surface has to charge up large enough to balance the currents. So what does this do to the surface, say? What if you're a blurry little astronaut on a blurry rover on the surface of the moon? Do you care about these large electric potentials? Well, I don't know. I suspect that the stuff that we're measuring with Lunar Prospector you probably don't care about, because even though it's a huge, huge potential drop, 4.5 kilovolts, it's probably over a large scale size. So the electric fields are probably not too big. But there's a huge caveat to this, because the stuff I'm talking about is basically global. It's the whole night side of the moon that we're measuring. But the same physics applies to some little localized boulder or mountain right near the terminator. On one side of this mountain, it's going to be plus 5 or 10 volts, photoelectron dominated. On the other side of the mountain, it can get pretty negative if it's dominated by these energetic electrons. So you might get some actually fairly strong electric fields right at these late dark kind of boundaries. And one place that this might happen is at the lunar poles, which is where we want to go. So I'm not saying that there's a hazard there. I don't know if there is or not. We actually want to model this and see exactly what happens in these kind of regions and find out if there is a problem. But there is at least a promise that there may be large electric fields there. One of the things these large electric fields may do is they may move dust around. So I'm going to finish up by talking a little bit about dust. There's a variety of evidence from the Apollo days that dust does get off of the lunar surface. And this is kind of varying degrees of controversial. Very non-controversial. Surveyor 7 images. You're basically in shadow behind the terminator. You're looking out towards sunrise, but it's still late enough at night, early enough in the morning, whatever you will, that you shouldn't see any sunlight coming over the horizon. Nonetheless, you see this big glowing patch of something here on the horizon. What we think is going on here is that sunlight is hitting a cloud of dust above the horizon, and it's forward scattering over towards you. So the sunlight is getting to you, even though you should still be in the dark. This is pretty uncontroversial. Everybody pretty much believes that there's dust levitating above the terminator to sort of meter scale heights. A little more controversial, this is an instrument called LEAM, the Lunar Ejecta and Meteorite Experiment, which was designed to measure ejecta and meteorites. But they measured something that was very strange. They measured large, slow-moving dust particles, and the distribution as a function of local time was very non-uniform. This is in terms of hours from sunrise, which is a funny kind of a unit. But basically, here's sunset. This is right at the sun shadow boundary. You see a big spike of these dust impacts. Here's sunrise right at the light shadow boundary. You see an even bigger spike of these dust impacts. Nobody can quite understand why this is, but there's at least some reason to think it might be associated with electric fields. And the reason for that is that it's right at this light shadow boundary, right where everything interesting should be happening in terms of the electric fields. So slightly more controversial, there's some questions about how this instrument operated. Finally, most controversial of all, these are astronaut sketches from Gene Cernan in the Apollo command module. As they're flying over the surface of the moon, similar geometry to this image. They're going from shadow into sunlight, and there's these sketches of emission that they saw. And some of this is coronal zodiacal light from interplanetary dust. That's well understood. But there's this extra component, these streamers that they saw, which a number of people have interpreted as being from high altitude dust, extending up to tens or even hundreds of kilometers. So as I said, that's the most controversial of all. Some people don't believe it's dust. Some people think it's sodium emission. There are questions about the scale height. The scale height seems wrong for sodium, but it seems hard to get dust up that high. But anyway, there's a lot of reason to think that dust may be getting up off the surface of the moon. It almost certainly is to a few meters, maybe to tens or even hundreds of kilometers. So why do we care? Well, the dust is basically just a huge pain in the butt for any kind of operations on the surface. This is another quote from Gene Cernan, the guy of the sketches on the previous page. You can see there's tons of dust on the surface of the moon. Anybody who's looked at astronaut photographs or any of these old archival materials, there's tons of dust. You step out of the command module or the lander, and you're sitting in dust. There's just tons of it everywhere. It was a huge problem for the rovers. One of the rovers, the fender broke off. They're driving around the surface of the moon, and they're creating a fountain of dust, which is shooting up above them and coming down and landing on top of the astronauts. They actually had to make a makeshift fender here out of some little procedure handbook or something and tape it onto their rover, because otherwise they're just getting covered with dust as they drive around the surface. This dust gets into everything. It's really fine-grained. It's really abrasive. It sticks to the suits really well. It clogs up mechanisms. It gets on any kind of machinery and equipment you have out there. Basically gets on everything. My favorite story about the dust was that a whole variety of different equipment failed because of the dust, but my favorite is that the vacuum cleaner, which was designed to take care of the dust, was clogged up and broken by the dust. So these are the kind of things that happen from dust. There's also some concern about toxicity from dust. The lunar dust is really, really angular and barbed. There's no water on the surface of the moon, so there's no alien procedures to smooth it out. It's just really, really sharp. It may also have reactive volatiles on its surface. Some of the Apollo crews reported a gunpowder smell when they got the dust into the cabin. So these are the kind of things that people are worrying about with the dust. And how do the electric fields fit into all this? We don't quite know yet, but if the electric fields are causing a lot more of this dust to get off of the surface, and if it really is as nasty as we think it may be, it's something that we need to be thinking about. So how are we thinking about this? Well, we're thinking about this through a Lunar Science Institute. Last year, as I'm sure many of you know, NASA decided it was going to do these new Lunar Science Institute teams modeled after the Astrobiology Institute. So at Berkeley, we proposed, along with Goddard and a few other institutions, to start a lunar science node called DREAM, Dynamic Response of the Environment at the Moon, which is pretty much the best acronym ever because we're the DREAM team. Thank you very much. So what we want to do with that is we basically want to study everything that I've finished telling you about now. And we want to study it as a coherent unit. So our mission statement is to find out how the highly variable solar energy and matter incident at the surface interface affects the dynamics of lunar volatiles, ionosphere, plasma, and dust. And we want to use that to guide future missions, et cetera, et cetera. You can read all this. But the most important thing is that we want to look at all this as a dynamic system, and we want to look at how all of it is coupled. We want to know how the exosphere is coupled to the ionosphere, how that ionosphere couples to the surface charging and the plasma sheath, how the exospheric neutrals and the dust interact. Dust may actually be a significant species in the exosphere, so how does that work? We want to know how the charged plasma interacts with the magnetic anomalies. Is there an effect on surface weathering, these little optical albedo anomalies that I told you about? And how is all of this driven by solar wind and solar energetic particles and solar UV inputs? So we're just getting started up now. It takes ages and ages and ages just to get our funding from NASA, but we're getting going, and we're really excited to look at all this kind of thing. As a lunar scientist, it's a really exciting time right now. There are a lot of lunar missions already at the moon or planned, ranging from a Japanese mission, Kaguya, which is already there. Similarly, an Indian mission, Chandrayaan, and a Chinese mission, Chang'e. There are probably going to be new missions from each of these countries following on to these. In the meantime, there's a number of missions which are going from here. There's Lunar Reconnaissance Orbiter, which is going to sort of map a whole lot of things on the moon which are important for future habitability, like water, temperature, topography. Secondary payload to LRO is LCROSS, which is being built right across the street at Ames. This is going to be a little impactor. They're going to impact it into the North Pole, see if they can hit one of these cold traps full of ice and send up a plume of water vapor that we can observe both from the trailing spacecraft and hopefully from terrestrial assets. So that'll be really interesting. Also, over at Ames, they're working on a spacecraft called LADEE, which will be stands for Lunar Atmosphere and Dust Environment Explorer. So that'll be looking at the dust and the exosphere and how that plays together. Finally, there's a mission that we're really excited about at Berkeley called Artemis. This is actually an extended mission of a mission called Themis. Themis was a magnetospheric mission that we built at Berkeley to study the aurora and substorms. It turns out that this original mission had 5 spacecraft. 2 of these spacecraft will not survive their extended mission in the magnetosphere because the shadows behind the Earth are too long. So our principal investigator, Vasilis Angelopoulos, had the bright idea of taking 2 of these guys and sending them out to the moon for their extended mission. So that's what we're going to do. They're going to be out here measuring the details of the wake structure, looking at pickup ions from the exosphere, looking at crustal magnetic field interactions, etc. So the moon's a really exciting place to be right now. There's going to be a lot of data. There's a lot of interest in it. I encourage anybody who's interested in lunar science to get involved in these missions. There's going to be more data than anyone can possibly analyze. Finally, to Mars. All the stuff that we're doing at the moon has huge applicability to Mars. This is kind of a view of space physics at Mars. And if you remember my original view graph from the moon, there's a lot of similarities. There's a lot of the same kind of stuff going on at Mars. There's an exosphere, which is much more significant at Mars because Mars actually has an atmosphere, but there's also an exosphere outside of that. There are these same kind of interesting processes with crustal magnetic fields, although, again, they're much bigger at Mars. It's being bombarded by the same kind of inputs from the sun, and there's all these similar kind of loss processes for the atmosphere and exosphere of Mars. But there are a lot more big picture implications with Mars, because Mars, we're pretty sure now, used to have a ton of water on its surface, but now it doesn't anymore. So how did the water go away? Well, one way it may have gone away is to space. I don't even want to get into the details of this flowchart, just to say that there are a ton of different processes by which this can happen, and it's really complicated. But we're going to try and measure all of these with a spacecraft called Maven. And so that's what's taking the kind of the other half of my time at Berkeley right now, in addition to this Lunar Science Institute dream. All right, thank you very much.
Do we have questions for our speaker?
Is the dust charged? Is that why it's sticking all to everything aside from its just fine-grained nature?
People think that that may be the case. The dust is certainly charged because everything out there in the space environment is charged. Whether that is why it is so sticky to astronaut suits and stuff like that, we don't know for sure, but we suspect that it probably plays a role.
Maybe clean.
Yeah, no, there are some wild ideas out there. I mean, people are talking about, basically having a little wand that like decharges your suit and then the dust all falls off.
If the dust is charged, then what might be happening in these regions where there's an intense crustal magnetic field?
Great question. Who knows?
Well, as a plasma physicist, what would you expect? Would you expect the particles to then be more trapped in that area and not be able to escape if they're being generated by surface impacts?
What I suspect is that the dust is big enough that the magnetic field probably doesn't do much in terms of controlling where it goes. I suspect that the dust itself probably doesn't really feel the magnetic fields. It's large enough that the electric field is going to be the main thing driving it, and gravity. But what I think is really interesting is that the dust might actually be a significant charge carrier in those regions. So you've got a big cloud of charged dust there. If the charge density from that is comparable to the charge density from electrons and ions, it may completely change how the solar wind interacts with these regions.
My second question was the Surveyor 7, the way in which those images were taken. Can you describe that again? Because I understand how the ZODI, if you're looking at towards sunrise, you would expect to see the zodiacal light scattering, and then it must be early enough that you're not seeing the ZODI. Is that correct?
Mm-hmm. Yeah, that's exactly it. You can't directly see the sun, but it diffusely forward scatters through this cloud of dust, and some of it comes over the horizon to you.
But you typically, from the ground-based observatory, you can see the ZODI like an hour and a half before sunrise, so even before twilight begins. So there's quite an extended period of time where you see that. But obviously, that structure wasn't in the Surveyor images. Which is more like a V shape, kind of like from the astronaut drawings, Gene Corvin's drawings.
So the Surveyor's not brighter than the zodiacal light? That's why you see the zodiacal light of the stars?
Absolutely. There's also an issue of scale size. The zodiacal light extends to very large altitudes above the surface. This stuff is right at the surface. It's a few meters above the surface, and it's very bright. As you pointed out, that's exactly right. They did some calculations of the brightness, and they, I I'm forgetting exactly the densities of dust that they came up with, but it was quite high. It was something like 10 to the 7 times too high to be explained by micrometeorite impacts.
You mentioned outgassing earlier, and I was curious if you could comment on current rates of outgassing from the moon. And to build on that a little bit, I was wondering if you could also comment on the effect on the exosphere and in the wake that a sustained human activities will have through outgassing and dust mobilization and stuff like that from human activities.
Great question. Current outgassing from the surface, we're not 100% sure it even exists. There are several measurements of alpha particles and possible detections of radon and polonium, but they're very low levels. It's probably a very minor contributor to the exosphere, if anything. Surface presence of humans, on the other hand, could be a huge contributor to the exosphere. Just as an anecdote, one of the Apollo missions released a whole bunch of gas, and it was a large enough signal that the instruments that they had on the surface that were trying to measure the exosphere couldn't measure the natural exosphere for weeks afterwards because the signal was completely dominated by this gas that was released by one of the Apollo missions. So this is one of the reasons why people are very excited to do missions like LADEE before there's actually a sustained presence on the surface, because these surface effects can be quite large. I mean, the total mass in the lunar exosphere is on the order of a few tons. It's really not very much at all compared to what we can generate.
Other questions?
You mentioned that sodium is only a minor component and it's studied because it has a good optical emission line.
Mm-hmm.
What are the other elements? Do they scale somehow to the average chemical composition, or is there selective sputtering?
Probably both, but the short answer to that is that we don't know. We've only measured 5 species in the lunar exosphere. Helium, argon. Helium and argon are really the only things that we have any idea of the dynamics of in the lunar exosphere. Sodium we've measured remotely. We really don't know what's going on. They measured. They had an experiment on the surface, which was basically a cold cathode gauge that measured the total exospheric density, and then they had these other detections of different constituents, and the constituents don't add up to the total. So there's a whole bunch of stuff there that we don't know what it is yet.
When you talked about the charge-induced migration of materials toward the poles, has anyone modeled the rate of that and how mass transfer rate, or how you predict mass transfer rate that way?
The stuff that I was talking about migrating towards the poles actually is not charged at all. It's just randomly hopping around, and it sticks at the poles because it's cold there. Dana Kreider has done pretty extensive modeling of that, and Rich Vondrak, but I don't have any of those numbers on top of my brain. I can't quote you any specifics.
What are the origin of the species that are coming off into the exosphere? What kind of mineralic components that are giving off these gases?
How many did I come up with so far? There's helium, there's argon, there's sodium, radon, polonium is controversial. There's one other that I'm forgetting. One thing that they haven't measured yet is oxygen. You'd think there would be tons of oxygen, but they haven't been able to measure that. Most of the other stuff they've only been able to set upper limits on. But the answer to your question is that it all comes from the lunar regolith, and the lunar regolith is just, basically a ground-up version of whatever the lunar crust is made out of, which is, plagioclase, feldspar, mare basalt. It's a variety of different mineralogies depending on where you are.
So it's just kind of buried ions or buried elemental species within the structure of the rock, essentially.
Well, it's generated by a variety of different processes, but basically most of it, you hit it with something and something comes off. So yeah, it's a little molecule or whatever from one of these minerals sitting on the surface.
Great. Let's thank our speaker again.